Welcome to the Bear Symposium. This is a really exciting event for us here at Berkeley because it's a chance for us to interact with you, our friends, collaborators, and sponsors. And it's a chance for us to show you some of the things that we've been doing. So to me, one of the greatest things about Berkeley is that we have a fantastic set of faculty and students that are all involved in really fascinating projects. And this morning, what we'd like to do is have 4 talks describing 4 of these projects. They cover very different aspects of electrical engineering and computer science, but one thing that I think ties the 4 of them together is that they all focus on the way technologies and methodologies affect and interact with people. So consider, for instance, electronic devices. They keep getting smaller and smaller, these days more and more wearable. And as we are building these smaller and wearable devices, we're starting to think about how to make the devices themselves flexible, bendable, so that they adapt to people. One of the people leading the charge in this effort to make flexible electronic devices is Professor Arias, and please join me in welcoming Professor Arias.
Good morning, everyone. Thank you very much for this opportunity to talk to you. What I'm going to talk today, I'm going to start with an overview of flexible electronics first, because I know that everybody here comes from different backgrounds. And this area really involves different types of semiconductors and things that are not the traditional electronics that we all study in our books when we are getting our degrees. Then I'm going to show you 2 different projects that serve as examples of how, when we start to change the form and the shapes of electronic devices, how we can enhance the measurements that we do from our bodies, and how we can start to understand a little bit more about how to monitor our health, but also how to image the different aspects of our body. So starting with the new semiconductors, there are several approaches that people are using in order to get flexible electronics. It always comes to the fact that you have to use a new semiconductor processing. You have to move away from the traditional silicon wafer. So there are people that are using, just changing the substrate, and now instead of using silicon wafers, we start using plastics. Literally, a plastic sheet is now the substrate that is carrying this electronic device. And then you change the process temperature. The way the ovens in the fabrication lab are operating are way lower temperatures than what is conventional. So now these devices are fabricated in plastic at only 150 degrees, and we all know that this is very low for semiconducting processing. Others stick to the high temperature, but they process on glass. And then after the fact, you just transfer the entire device into a flexible substrate. This requires a little sacrificial layer, but by using laser, you can pick up the entire backplane for the display, or the circuits that you had in the glass substrate, and now transfer to a flexible substrate. And we start seeing displays that are flexible, that also have the front plane, the display media that is also flexible. This is now done by PVI, and in fact, our e-reader books have the flexible backplane and the flexible display. Everything else is rigid, the drivers are rigid, but the display is now flexible. Some people really don't want to get rid of the silicon wafer, so one approach is just to make the silicon as thin as possible until the silicon itself becomes bendable. And there has been examples where people try to make flexible solar cells where you just thin down the silicon wafer, and you can see here that you can roll the silicon wafer. This approach has been used by many people just trying to make from high-speed electronics to displays, just thinning down the silicon. All about changing the process of the semiconductor. And of course, the entire new category of semiconductors now is by using semiconductors that they themselves are flexible, such as organic molecules and polymers. So this is what organic electronics is all about, which is very fitting for Berkeley, of course. Basically, these materials, as we know them in our day-to-day life, we know them as flexible materials, but now they have new properties. They can emit light, they can absorb light, and they can also carry current. They are a very good they are good semiconductors, different from silicon. So when you start looking at organic materials that are inherently flexible, there has been several applications that people looked at, and you see that these materials can be processed at a large area. So they became interesting for large screens displays. And today, Panasonic, LG, and Sony have shown a really large area and start to be flexible displays. Also for lighting, these materials, these organic semiconductors, they emit light in all wavelengths of the spectrum. So you can also get white light. And people are looking at how to start integrating these new types of light-emitting devices into the building so that we can have different ways of lighting the environment. In terms of thin film transistors, these materials have also been used for backplanes and for making circuits. You can get materials that behave as P-type and behave as N-type. So now you can, we just started maybe 2 or 3 years ago seeing circuits that are comparable to many applications, or they are compatible with many applications that we have, because you can make CMOS based on these organic semiconductors. And of course, photovoltaics, as I said, they absorb light, so you can also make photovoltaics. And you can see here that you can produce really large sheets of devices with different functionalities. In terms of manufacturing, these materials are also revolutionary because now you can think of your semiconductor as an ink. In fact, this is a selection of light-emitting semiconductors, and you can see how here is the powder being very fluorescent. But when you make a solution out of it, it also emits lights, and this is what we use in order to make these devices that are truly bright and a very true color. Why is the manufacturing different now? Because now my semiconductor, as I said, is no longer the silicon wafer that I get in the box and I process throughout. I am really building my device from solution. I am printing, or I'm depositing every layer the same way that I was depositing the photoresist in a traditional processing. Now I actually deposit the active layer, the functional material from solution. For manufacturing, people are very excited about this area because you can imagine that the holy grail of this area is that you would get electronics in a row-to-row fashion, where in one side of the machine, of the row-to-row machine, you have an empty plastic row, and on the other side, after it's gone through the process, deposition by deposition from solution, you get your electronic device. That electronic device can be a display display, could be a solar cell, or could be integrated circuits with sensors. So this is what drives people into this area. Completely different manufacturing facilities. Why is that interesting? Of course, it has the promise of really fast throughput. It can be highly customized because you can change your design. So with the same set of tools, you could print different final products. You just have to think, the way I think about this is like a print shop. So today, if you want to print catalogs, you go to the print shop and they'll say, okay, which kind of paper do you want? Do you want glossy or not? Do you want color or not? Do you want black or white? So the same thing could be done for electronics now, where you can say, I want it to be flexible, I want it to have amplifiers, sensors, and I want to do this at the end. So that is really the vision going forward in manufacturing of electronics. We are far from there, but we are moving towards it. So you have to ask yourself the question first, and I'm sure in this room there are lots of people already thinking, oh, but I know this process, I could do this flexible, if I do it small enough, it will be flexible. This is all true. We have to think about, when do I really need to be printed in order to move forward with the right processing and the right development. So one thing that I believe is that large area electronics, it has huge advantage if you can print these devices. Just because it's large area, it's easy to print. We can print sheets of newspaper, so why couldn't we print the electronics at that scale and that fast? But I also think that printing is very good for distributing electronics. So if we think about applications where I want to distribute sensors and have localized electronics or electronics near those sensors, but I want to distribute over large area, you can do a combination of printing and pick and place in order to distribute the electronic and print the interconnects. So at the end, you end up with a large sheet that is just sparse electronics. That's something that's quite difficult to do today. Of course, I told you that the holy grail is monolithic in fabrication, but I believe that there is space for heterogeneous integration, where you use printing to deposit certain devices, and then you can always add silicon ICs to where you need the fast computing, where you need the fast electronics, which is something that it's not easy to use right now with printed electronics or flexible electronics per se. So when does it need to be flexible? As I said, large area electronics, I think being flexible is also helpful, and you can see all the development on displays. Why? Because manufacturing is easier if it's flexible. Also, transportation is easier, and installation is easier if it's flexible. But I really believe that whatever is in contact with the human body has to be flexible. It doesn't matter if it's going to be in contact of my skin or inside the body. Being flexible is a must, because our tissue is flexible and our clothes are flexible. So if we are going to have more and more wearables where it seems to be the trend, we need to make these devices flexible and more integrated with us. So what are we doing in my group? We started off by saying, okay, one thing that everybody wants to do is to monitor health signs. So I want to monitor, when you go to the hospital, the first thing that they connect to you is a little blood oximeter that's going to measure your oxygenation. It's in your finger. It has LEDs and one photodiode, and then it's connected to a bunch of machines that are measuring and processing that data, extracting the data, and processing in a way that it can be a meaningful information about you. So what do you get? You get ECG, you had pulse oximetry, you get your respiration rate, blood pressure, and temperature. Those are the vital signs that are monitored when you are in the hospital. Now, there are devices that we can also wear when we are exercising that will monitor certain things, not necessarily all of them, but will monitor and give us an indication of how healthy we are. Well, it turns out that this measurement, this simple measure, blood oximetry, it's a very noisy measurement, and that's why the electronics is so complicated. And why is it noisy? It's because you only have 2 little point sources of light and 1 photodiode. You are measuring the transmission of light through the tissue and through your blood. And then you pick up a very tiny AC signal that is on top of a huge DC signal, which is AC because we are measuring the pulsating blood. And from that AC signal, you try to make out your data and extract the data of oxygenation and pulse rate. Well, you need different wavelengths because basically you are doing a ratio of absorption in 2 different wavelengths because the oxygenated blood and the venous blood have different extinction coefficients. And you have here, what I'm plotting here for you is actually the ratio at different wavelengths. And you can see that throughout the spectrum here, there are several places where the ratio is quite high. So of course, you want to do your measurement at those spots where the ratio between oxygenated and non-oxygenated is very high. Well, if you can do that, then the whole system it looks more like this, where you have the devices, which are the light-emitting diodes and the photodetector. You have some analog circuits that will do the conversion and the processing. You always need microcontrollers. You're doing a lot of computation, and then, of course, visualization. We humans need to read the results somehow. So what I think in terms of flexibility, what needs to be flexible, what needs to be wearable, is that we could easily make the devices here and some of the analog circuitry flexible. We could transmit the data via RF, so that via wireless, so that we don't need to have those wires coming out of us anymore. And of course, this could be displayed in a computer, could be displayed on our cell phone. It depends on the setting that you are at. So we took this problem and we said, okay, let's make this a wearable device that is flexible. And we worked a lot on this part and also in the design of the system. So in terms of LEDs, which is the light source, now we have a process where we can make flexible LEDs. Oh, this is so weak, I'm sorry. That actually give light in 2 different wavelengths. And these wavelengths, believe me, give the high ratio that you need to do the measurement, the oxygenation measurement. We also developed the photodiodes that are flexible when printed. You can see here, I like to show the efficiency. The efficiency is not as high as you would have for a solar cell, for example, or even for a silicon photodiode. But that doesn't matter. What is important for this application is that the broad absorption of these materials allow me to do the measurement in different wavelengths and pick up all these ratios that I need in order to do this type of measurement. So today, we can measure this in our labs. If we take the silicon diode out of the equation and do the measurement with conventional LEDs, this is the type of data we get, where you can see here the pulse rate. You can extract the heart rate. You can extract the oxygenation. And then when we take the LEDs, the inorganic LEDs out, and we replace by either red or green LEDs, we can do that type of measurement. You can see here the spectrum is not as as clean as before, but this is something that we believe it can be improved. Well, like every project, we started by trying to say, okay, let's do that better, because I really believe that we could do it. But talking to doctors, actually what they want is something that they don't have today, which is to be able to monitor not only the central oxygenation, which is what that device in your finger does, but actually to compare the central oxygenation with localized oxygenation for surgery recovery. So whenever we have surgery, the only way that doctors know if the skin around the surgery or if the tissue where the surgery was performed is surviving or if it's doing well is by having a nurse go there and look every now and then and say, oh, it looks good, oh, it looks bad. And when it looks bad, it's too late. So what they want is to have a device or a blanket that is flexible or a bandage that is flexible that can cover a large area of the body and it can map the local oxygenation. So imagine doing this with the current technology. You would need so many LEDs, so many photodiodes, it would become so expensive that people wouldn't be allowed to use in the hospital. But with the printed electronics and the large area aspects of being able to distribute these devices over flexible substrates and large area, we believe that we can do this measurement. And you can see we can provide this for the doctors. So we are adding to our bandage, we are measuring ECG, we are measuring temperature, and the local oxygenation as well as the central oxygenation. We had to change the design. We are measuring now by reflection instead of transmission, but this is very exciting work that we are doing in partnership with UCSF. Okay, I'll change gears. I think I have a few minutes left. Now, imaging. Imaging, it's something that's also important, not only to monitor, but for diagnose. And here, in this project, I work in collaboration with Mickey Lustig, who is a professor in ECS, and he's a specialist in MRI, and everything that I am presenting here, I really learned from him. But his research is more focused on the imaging and how to process the data in order to get the image faster and better and so on. So when I joined the department, we started talking and we said, okay, he told me the biggest problem we have with MRI is that the hardware that we use for the imaging doesn't fit the body. Do you think you could do this with flexible electronics? I said, maybe. So we talked a lot, and we came up to, of course, I'm talking to you, so it works. So first, let me do a disclaimer. This is an MRI machine. When you go and do an MRI, you lay down here. Here's the big magnet. On the table, there RF transmit coils. And this is not what we are making flexible. You still need to go through the tubes, sorry. You still have to go there into the big magnet. But when you do get prepared for MRI, this is how you look like. They put a bunch of coils on top of you that are the receiver coils that are going to communicate with the coils that are on the table. And these receiver coils don't fit the body very well. They are very heavy and they are offset. Why is this a problem? So the MRI signal is another one that is very, very small. So if you place the coil very close to the skin and it fits, so I'm using here the spine as an example because it's so curvy and difficult to fit. So if you put the coil very, very close to the skin, you get very good signal to noise ratio, and this is a good image. Now, if you offset that coil just by 3 centimeters, and most of the coils are offset by your body by this much, you see the loss on signal that you get just by this offset. So what are we doing? Our design, or our project is called Bespoke Coils. We are funded by NIH to do this. And our idea is that, okay, so if I can print these coils, these RF coils on flexible substrates, why not print on the clothes And why not have a design that fits t-shirt sizes? Because we all know our t-shirt size. So when I go to the hospital, I say, okay, my t-shirt size is small. They give it to me. I know it's going to fit my body. Same for everybody. And especially for children and babies, this is a big problem because the hardware is so heavy. In some cases, they can't use it. And in other cases, they need to give a general anesthesia to the kids because the skin gets so long because the hardware doesn't fit. So this is our goal. This is where we are targeting. Get flexible MRI coils arrays that are completely conformal to the body. So, okay, in order to do that, there was again a lot of materials development and processing development, especially to get capacitors that can be printed on these flexible substrates and at the same time communicate with that big machine, the big MRI machine. So there are two types of capacitors. One is a tuning capacitor that you are going to use to set the resonance frequency, and that comes from the machine. Clinical MRIs have two types of clinical MRIs, either 1.5 Tesla or 3 Tesla. So you need to tune to that resonance frequency. And we also have matching capacitors that need to be tuned to they will set the input impedance, and that is a tuning that happens whenever you are going to take the measurement, because we all have different MRI signal, so there is a calibration that happens just before the imaging takes place. Okay, so we had to work a lot on the dielectrics and printing dielectrics. So we did that by blending now. We took two solutions, two inks, and we mixed them. We know they have different dielectric constants. We mixed them to vary the dielectric constants so that we could hit different resonance frequencies and provide these coils to whatever machine the hospital might have. We are even thinking about going to some of the research machines that operate at higher fields. How well do these coils perform? So the first thing, we have to connect now to the conventional electronics that's needed. And then we see if we can tune. This is the first thing that we have to do. We have to see if we can tune. This was designed for 1.5 Tesla, and that operates around 64 megahertz. So you can see here that we can tune to the exact frequency that the machine needs. But the ultimate testing is really imaging. And we do that either at Stanford or at UCSF. With our collaborators. This is done at Stanford. It is our collaborator, and this is my student. Here's the phantom, which is basically mimics the chemistry of our body. And you see that we place it's round because we want to make sure that the coil is conformable. And we just place there, and then we compare these coils to traditional coils. So you're comparing here 3-inch coils with these printed coils. This is a phantom made by GE, so you can see here that the image is very comparable. Of course, we measured the SNR, and now we compare the SNR with traditional coils versus printed coils. And we want to be true, and we only pick traditional coils where we can fit to the part of the body that we want to measure. And we see that we have about 20% loss on SNR with the printing. That comes from the materials not being as good as the traditional conductors. But if we offset and we make that like a real life situation, the printed coils perform better, way better. The fun test, of course, there's a student, there's an MRI machine, this is inevitable. So, of course, he said, oh, let's get image from my knee. So there it is. You can see how this is done. I find this amazing. It's a piece of plastic with 3 layers of printed materials. And then we connect it to the machine, and off he goes. And these are the type of images we get. This is a very healthy 23-year-old knee. Of course, the image is much better here, but I think you get the point. We are now at the stage in this project where we are expanding to make arrays and really fit a large area of the bodies, like I showed you in the t-shirt case. So stay tuned. I'll stop here, and of course I have to acknowledge the people that give me the money so we can do this work, and all my students who have contributed somehow to these results. And of course I have many collaborators at UC Berkeley and outside UC Berkeley that also contribute to the work. Thank you so much for listening.
So we do have time for 1 or 2 questions while we set up the next speaker.
Okay.
Please come to the mic here in the center.
I'm Zhenhua from Caltech. So one of my advisor, Professor Stephen Low, actually graduated from Berkeley. So my question is, for medical devices, I completely agree that flexibility is very important, but another factor is the size, right? When we make the device smaller and smaller, concerns emerge for the quantum effects and also the heat dissipation. So can you comment on the manufacturing advance to help this concern, to help to solve this concern? Thank you.
Sure. So if I understand your question, well, you were asking about reliability, and when you make smaller and smaller.
Not just reliability, one is for the heat dissipation is more related to the reliability, but the other is that for the signal. Like
for the signal, okay.
Like the microchips developed by Intel, they worry about the quantum effect there.
Okay, yeah. So I think there are different types of devices that you need. There are devices that you do need the devices to be smaller and smaller, especially for implantable devices. Other devices need to be larger area and still maintain the flexibility. So I don't think this technology is well suited for miniaturizing the device, but it's very good for mapping larger areas of the body. You have to pick the application to which you are going to develop. So, for instance, the mapping of the blood oxygenation is very applicable for ulcers, bad ulcers, and things like that, that you really need to monitor and compare different parts of the body. Now, the tiny devices that are implantable and people swallow and so on, it's very hard to get the resolution with this technology. So I would stick to silicon in that case.
All right. Thanks again.
All right. Thank you.